Have you written a real linked list or just that basic kind with no proofs? I'm Ray Myers. Welcome to Craft versus Cruft. And this is just a continuation of the previous episode on provable linked lists. So we quickly established this one-liner data type to hold a singly linked list in the programming language Dafny, which has proof support in it, and implemented a couple of verbs on that, namely getting the length and getting the ith element in a couple different ways. In the case of length, proving equivalence between the different implementations. So we're going to wrap this up today and then get back to our regularly scheduled programming in 2024, the year of formal methods. What else have we got? So we've got contains. What is, first of all, its signature? Contains type T takes a list of type T and then I guess an element of T. We don't have that requires anymore, but we are going to do this match. So handling case nil. If we get all the way to the end, then I feel like this would return false. And if it's a cons with a head and a tail, then one of two things, right? Head is either equal to element. We'll say if head equals element, then obviously true, else we recurse. You see these are all looking kind of the same. These recursive patterns, they repeat a lot. Does the tail contain the element? So what is it saying now? Okay, equals can only be applied to expressions of types that support equality. Now this is true. So this isn't going to do pointer equality here or anything like that. It has to know how to compare T. And it's just a completely arbitrary type. It might not be a type we know how to do equals on. But I can easily just say, okay, this has to be a T that has equals on it, and then we're happy. And it just won't let me call it on something I can't call it on. Now, I haven't proven anything about this, right? So I could just return false every time, and no one would be the wiser. So we're not using our full capabilities here. How would we specify this? What am I trying to say? I'm saying that if something is contained in the list, then it should exist somewhere in it. Do we know a way to do that? Well, we've got this function here, so we could express these in terms of each other. I should be able to get something out if the list contains it, is basically what I'm trying to express here. So that's the spec I'd like to write. Ensures contains li el implies. So if the list contains the element, that implies, or we could even use a double directional implies, that's interchangeable with saying that there exists some I such that get the ith element of li equals the element we're looking for. And as you can see, like, it can't prove that. I think that it is true, but we just don't have, we just haven't given the verifier enough to go on. And I think you would need to use lemmas if just given the definitions on the table, we were going to do that. And I'm not very good with lemmas yet. So stay tuned for that one. But we could just do good old-fashioned tests using, the ghost method, as I mentioned. So I'm going to punt on that for now. Let's implement another verb. Insert and delete is all we've got left to implement a linked list. Insert, what do we need to give? We need to give a list as input. We need to give the element to insert. And probably in the second param, I'm going to put the index, there's a nat, to insert it at. And this is not going to need to, well, I was going to say not going to need to return anything, but it's not going to modify its argument. So actually it's going to need to return a whole linked list. This is going to be interesting. This is going to be the first thing that actually transforms the list into another list. If you're in a purely functional data structure and you want to modify something, you actually need to return an entire new data structure, or at least a partially new one. You might return something that has, a fraction of the original and is just reconstructed a part of that, as we're going to see now. So that means the type that the function returns is also a list of T. list, let's look at the index. If I equals 0, then we want to attach this element right here. So that means that we have a pretty simple case, I think. We just need to make a console out of the element we want to add. As the tail of that console, we append the existing list. So we've inserted it at the beginning. And we can use the existing list in our new one, again, because these are immutable. Else. So we need to recurse then in this case. We need to make a console of the current list head. And as the remainder, we're going to do an insert on li.tail I minus 1, going to that next element, and the same element we want to insert. Now, this is going to be a problem. So what's going on here? Okay, yeah, it's angry because I said this needs to be tail recursive, and it can't make it tail recursive, and that's actually true. So this is not tail recursive. If we wanted it to be efficient, like we did earlier, we could do a by method implementation and prove that the functional one matched it. Now, what else is it upset about, right? Head doesn't match every kind of list. It only matches the console. So this is a case where I might have a nil element in the wrong place, right? Because you have no constraints on I could be long enough to walk off the list once again. Well, I think we're good on that because we can use a precondition just like we did before. So requires. So we just want to say that the length of the list is greater than or equal to I. Right, okay, so suppose that the length is 0 and I is 0. Well, then that's okay. We can do a console and append nil to the end. But yeah, if it were any less, then we're not okay. So yeah, now this will work. It will not blow up in any cases. And we have all these different verbs. We can start defining them in terms of each other, right? Because insert should have an effect relative to the length of the list, shouldn't it? Pretty well-defined effect. So we can do a post condition. Ensures that the list we get out is going to be one longer than the list we put in. That should always be the case, right? So insert li I el, whenever the arguments are, that the length of that is equal to the length of li plus 1. Very nice, very nice. What else should be true? Well, if we're inserting it into the list, then obviously the list should contain it after, right? Contains insert IEL EL. All right, great. So we've gotten a lot of compile time verifications here, right? First of all, any caller of this, it's going to make sure that it's calling it with an appropriately bounded index. We're also proving that this code, whatever it may do, it definitely increases the length of the list by 1, and it definitely gives you a list that contains the element you wanted to insert. Now, there are some other properties that aren't checked here, right? Like, did it put it in the right spot? Or did it not mess with any of the other elements? Did it like reorder them or something? If you want to completely specify things, you have to get a little more detailed, but nonetheless, very high degree of assurance being given here. We can go even a little further pretty easily and use get on the results of the insert and say, like, if I look at index I, after I've tried to insert this element in index I better get that element out of it. And again, that works. And the fact that we're able to mutually specify these verbs kind of against each other, that does give us some assurance that these other definitions are probably, right as well, because all the relative properties are holding. So just slightly different from the insert is the delete method. You have to, no matter where you're deleting something from, pretty much reconstruct the entire list from the head if you're going to do that. Otherwise, it's a pretty similar implementation. I'll leave that as an exercise to the reader. Another thing I'll note here, because I'm presenting functional programming as being able to solve this whole linked list problem very well, very high assurances. We're not tripping over any missing pointers or anything. But what if instead of a singly linked list, it were a doubly linked list? Well, it would not only be more difficult, but in a purely functional style, you just can't do it at all. You can do it in Dafny, but not in functional style. You need mutable state to even construct a doubly linked list. So in fact, if you're using purely functional data structures and you wanted to get a double-ended queue, they need to resort to things called finger trees and who knows whatever else in order to get that same behavior that you would just do with a doubly linked list. An interesting result involving formal methods and a doubly linked list, though, was in the Key project, which expands on, I think, OpenJML, Java modeling language, to use formal proofs in Java code. They did a verification in the Key project of the linked list implementation in Java, which is doubly linked. And they found a bug in it. They found an int overflow. And so there was a security critical portion of the JDK that actually had to change its implementation as a result of that to use something that didn't have that bug. The Key project also found a bug in, I think, collections.sort, the TimSort implementation that's in the JDK, and the same bug was present in Python. Well, I think we'll wrap things up for today. Links in the description as always. May all your pipelines be green, and as Lao Tzu said in the Tao Te Ching, with patience, the most tangled cord may be undone. Thank you.